Hi, I'm Daniel, and today we're talking about the Pythagorean Theorem, and there's more to talk about than you might expect. I've got two goals for this video. First, I'd like for you to come away with a better appreciation and understanding of the Pythagorean Theorem, and then secondly, I want to model for you how you might trace a mathematical idea or a formula through not only its development, but also through the many ways in which these things appear and reappear as we study math. So first, I have to point out that there's a lot more to the Pythagorean theorem than a squared plus b squared equals c squared. And we know that this relationship governs the squares on the sides of a right triangle. That's fine. But there's so much more to say than just this. And so I want to take you to Euclid for just a moment, and we're going to look at Euclid's proof of the Pythagorean theorem. But before we do that, there's two other things you have to know. First, you have to know that what we often refer to as the side-angle-side theorem or the side-angle-side postulate. If you've got two triangles, pretend that that's a triangle, and they share a side equal to a side, an angle equal to an angle, and then another side equal to the other side, then these triangles are congruent. So if this side's equal to this side, this angle is equal to that angle, and then this side is equal to this side, then we've got congruent triangles. Okay, so that's simple enough. There's one other thing, and this is a proposition Euclid gives. This is proposition 41 in book 1 of the Elements. But basically what he explains is that if you have a triangle and a parallelogram in the same parallels and on the same base, okay, so meaning that if they're in the same parallels, which means that here are the parallel lines, right? If they're in the same parallels and on the same base, there's our base, then the triangle is exactly half the area of the parallelogram. Okay? I'm not going to explain it. I'm just going to tell you that's the theorem, and it's true. He proves it. But the triangle is exactly half the area of this parallelogram. Okay, now we can take a look at Euclid's proof. So you might have seen a proof like this in geometry, right, where you have a right triangle, and we know that if this is the A side, this is the B side, this is the C side again, that the square on the A side, right, plus the square on the B side is equal to the square on the C side. That's how that works. A squared plus B squared equals C squared, right? Well, here's Euclid's proof for that. So he has us draw out this figure. We're going to add a parallel line, a line parallel to the base through that point. You'll see why that's important in a moment, and then we're going to draw a couple other lines. I'm not going to actually present the full proof to you just for the sake of time. I'm just going to talk you through. This is the Spark Notes version of that proof. That's what we're doing. Okay, so Euclid says, all right, we have this figure. We know this is a right triangle. We've built the squares on the sides. Now all we have to do is prove that this area plus this area is equal to this area down here. How do we do that? Well, remember the side-angle-side postulate or theorem. Well, we have two triangles right here. See that? There's a triangle there, have another triangle right here. Now, these triangles are congruent. Why? Because they have a side equal to a side. See that? An angle right there equal to an angle. I'm not proving that those angles are equal. Euclid does do that. I'm just telling you that they're equal for the sake of time. But then we also have a side here equal to a side there. So what we have is a side, an angle, and then a side equal to a side, an angle, and then a side, meaning that both of these little skinny triangles are congruent. Oh, but wait a minute. Remember that a triangle on the same base as a parallelogram and a square is a type of parallelogram. If they're in the same parallels, which they are, then the area of the triangle is exactly half the area of the square. Oh, okay. But wait a minute. The areas of the triangles are equal because they're equal triangles, which means that this parallelogram here, right, which is really just a little rectangle right there, is double the area of this triangle, which is in the same parallels and on the same base, which means that the area of this square is equal to the area of this rectangle. Got it? Okay. Now he does the same thing on the other side. So we're going to draw a couple more lines. Okay, so here's what we do now. Do exactly the same thing. So we have a triangle right here. Okay, here's our little green triangle. And we're going to prove that it's equal to this triangle right here. How do we do that? Well, we have a side equal to a side, because remember, this is the sides on a square are equal, right? We have an angle, and again, I'm not going to prove that the angles are equal. I'm just going to tell you. That angle is equal to this angle down here, which Euclid does actually prove. And then we have a side equal to a side there, because again, the sides on a square are equal. So we have a side, an angle, and a side equal to a side, an angle, and a side. Which means that the triangles, right, are equal. So that one's equal to this one. They're congruent triangles. Oh, but wait a minute. We have, as it turns out, a parallelogram here, right? Parallelogram on the same base, and I'm going to switch colors real fast to make this more visible. Parallelogram, right, on the same base as our triangle, and in the same parallels as the triangle, which means that this parallelogram is twice the area of our triangle. Oh, but the triangles are congruent. Okay. And look, lo and behold, we have another parallelogram right here in the same parallels as this other triangle, right? So this parallelogram right here is double the area of this triangle, which means, of course, that this area must be equal to this area here. So what we've done is we've shown that this square is equal to this rectangle, and this square is equal to this rectangle. So we've actually shown that the sums of this square plus this square is equal to this entire square. That's Euclid's proof in a nutshell. It's great. It's a really good proof. It's not the only proof. There's lots of proofs of the Pythagorean theorem, but this one is my favorite. Okay, now, brace yourselves, because we have to make the jump forward a couple thousand years or so to Descartes. So what does Descartes do? Well, he introduces, right, the Cartesian coordinate system. That's why we call it Cartesian, after him. So you'll remember we've got, our y-axis, we have an x-axis over here, and so on and so forth. Now, we're taught something called the distance formula, right, which is a way of determining how long a line is on our coordinate plane. So the way that we do this is we have an x and a y value here. All right, there's some x and y value there. And I'll do this one in a different color just to visually separate it. And then we have another x and y value there. Right? And then what we do is we use this formula, which you've probably learned something like this. Right, so d is equal to x, 1 or 2, doesn't matter which one it is. So one of the points minus the coordinate for the other point, plus the y value of one point minus the y value of the other point. You take the square root, and that's the distance of those 2 points. Now, what does this have to do with the Pythagorean theorem? Well, it is the Pythagorean theorem. Right? Well, how do we know? Well, it's because this is the hypotenuse. And if you're paying attention, you might have noticed that what we've done here is essentially this. We've completed the triangle, like so. And the difference of the x values, so if we call this x1 and this x2, right? That would be x2. Then the difference of those values, which is here, gives you the length of that side. And then we've squared it, right? So just to make this clearer, let me go ahead and square both sides of this. And I just realized that everything I'm writing is not even on the screen. So sorry, hang on. Let me move that over so you can actually see what I've done here. Okay, there's the distance formula. So what this means, right, is we have this. So if I square this whole thing, just so that you can see what it looks like squared. If you square it, you've got d squared is equal to the difference of the x values, which we're just going to call x for now, x squared, plus the difference of the y values, which you might just call y. That's the y value there, right? Difference between this one and that one. it's the same thing as the Pythagorean theorem. But there's more that we can say, because this isn't where the Pythagorean theorem stops being useful. Circles. What does a circle have to do with triangles? Well, let's find out. The equation of a circle is x minus h squared plus y minus k squared equals r squared. All right, so what does this mean? Well, so hk just gives you the center of the circle, right? So hk is simply the center of the circle. Which means that if the circle is centered at 0, 0, like it is here, what you actually have is x squared plus y squared equals r squared, which should look suspiciously like the Pythagorean theorem, because it's the same thing, right? The only difference is that rather than talking about a hypotenuse, we're talking about a radius. How does that work? Well, it's because the radius of the circle here actually traces out the circle by producing, theoretically, an infinite number of right triangles. I'll explain how that works. So what we have is, if the red bit here is the radius, and I'm going to complete the right triangle so you can see it. If I have that right triangle right there, think about what we're doing. We're keeping the radius the same because that's not moving. That piece isn't changing. What we are changing are the x and y values. And so what we're doing is we're solving the equation for every conceivable x and y value, which in combination give you our set radius, whatever the radius is. And so if the radius here is, say, 4, then of course we would have 4 squared or 16. And what we would be doing is we would be looking at all the combinations of x and y, which in this formula add up to give you 16, right? So literally what we're doing is we're taking, we're drawing, I'll do it on this side just so I won't clutter up the diagram too much. We're drawing an infinite number of triangles, right? And the radius is going to be the same for all of these triangles. So we don't have to worry about that, but the x and y values will be slightly different as we go around, right? But we keep doing it, and we keep doing it, and we keep doing it, and you do this forever, and you end up tracing out a circle. And if you're wondering, wait a minute, but what about the negative values? Because if you go down here into this quadrant, you've got some negative values. Well, don't worry, the negatives are taken care of. Why? Because everything is squared, and you know that a negative times a negative is a positive value. So you can still do this in the quadrants where you've got some negative values, right? So because you've got negatives in the second quadrant, third quadrant, as well as the fourth quadrant. So you can work all the way around. And when you do this, you trace a circle by following where the radius is going for all of these different values of x and y. So as it turns out, the Pythagorean theorem, which is establishing relationships between the sides of a right triangle, gives you the distance formula. That's pretty useful. But the distance formula is also a form of the equation of a circle, which is great. I mean, it's fantastic. So how many triangles does it take to draw a circle? Well, the answer is like theoretically an infinite number, but they're all right triangles, right, based on the Pythagorean theorem. Okay, but that's not even where we have to stop, because there's one more thing I have to share with you. So if we have a triangle like this, okay, just pretend that this is a right triangle. Here's my right angle. All right. This is something that Euclid proves in Book 6 of the Elements. It's proposition 31 in Book 6. He proves that if you have similar figures built on the sides of a right triangle. Okay, so we're just going to draw a rectangle there, another rectangle over here on this side of our triangle, and then another rectangle up here on this side of the right triangle. Now he proves that as long as they are similar figures, meaning that the ratios between the sides are all equal, right, and that the corresponding angles are equal, then the relationship which was presented in the Pythagorean theorem still holds true, which is to say that the area of this figure on the short leg, or this leg here of the right triangle, plus the area of that figure on the other leg of the right triangle, you add those areas together and they're going to be equal to the area on the hypotenuse, the similar figure on the hypotenuse. Now the crazy thing then is this is basically the Pythagorean theorem, but not with squares, which means that the Pythagorean theorem is actually a very specific instance of a broader principle, which is this one. And the reason the Pythagorean theorem works is because all squares are similar to each other. So that means, this is where it gets pretty crazy and loads of fun. If you have a right triangle, okay, there's my right angle, you can draw any figure on the sides of a right triangle, and as long as all the figures are similar, this still holds true. So if you wanted, you could, just using a compass, you could draw a semicircle on every side of your right triangle. Pretend that that's a semicircle. And if you do that, then what you have to say by proposition 31 from book 6 is that the area of that semicircle plus the area of this semicircle is equal to the area of this larger semicircle. And why does this work? Because all semicircles are similar to all other semicircles. Isn't that great? So that's the Pythagorean theorem, maybe like 4 different ways, 5 different ways maybe. But I just think that it's one of those theorems that's so powerful and so fascinating because it appears and reappears all over the place. And then in the end, you discover, wait a minute, it's actually just one specific instance of an even broader principle, which is relating the areas on the sides of right triangles. So that's going to be it. Hopefully that was interesting. If you enjoyed this, please consider subscribing. Check out my website as well. I'll put a link down in the description. Thanks for watching. Bye.